Okay, let's take a look at the 2011 scholarship paper, question 2. I found this question very straightforward, both parts A and B, for a scholarship question. So it just goes to show you that some of the questions can not be too bad. This question here is all about differences in melting point and ability to dissolve in water of 3 different compounds. And the question is, part A, account for the differences in the properties of the compounds in the table below. So the 3 compounds are given. 3 compounds are cyclohexane, which is an alkane. So pure hydrocarbon. The next compound is cyclohexanol, which is an alcohol. And then you have cis cyclohexane 1,2-diol. So this is a diol and has 2 OH groups on it. So straight away from even level 2 organic chemistry, I know that alkanes are insoluble in water, which is verified over here in the solubility table section. Alcohols are sparingly soluble in water, depending on how big they are, and also on the number of OH groups that they possess. So the reason why cis cyclohexanol is very soluble versus cyclohexanol is because of the 2 OH groups. So not a very difficult question at all, really. The melting point difference then is also due to the strength of the intermolecular bonding. So solubility is due to polarity of the compound, and the melting point is due to the strength of the intermolecular bonds. So I just wrote this statement down. The solubility of a solute, which is either of these 3 compounds, is dictated by the compound's its ability to break the intermolecular bonds that exist between individual water molecules. So the individual water molecules, if you want to dissolve in water, then you need to be able to break those bonds that hold the water molecules together. Now, if we draw 2 water molecules, the individual or the intermolecular bonds we're talking about here are hydrogen bonds. So it's hydrogen bonds. In terms of intermolecular bonding, hydrogen bonds are one of the strongest, and therefore, in order to break them, you need something which can compete with those hydrogen bonds. So this is possible for the 2 alcohols, because with the alcohols you can compete with those hydrogen bonds, whereas the alkane has no chance. So also, water is a polar solvent or molecule and likes to interact with polar solutes. So if we just lay out the page like this, we just put some comments down for each of the 3 compounds. So cyclohexane is here, and then we have cyclohexanol, not spelled very correctly, but that's the cyclohexanol. And then we have our cis cyclohexane 1,2-diol. Okay. So one thing I've started to do with answering these questions as well is to actually give yourself a bit more time to get through the paper. I've started to use a lot of shorthand because it's physically impossible to get through these questions in the 35 minutes allocated if you start writing lengthy explanations and don't use shorthand wherever possible. So I think this is the expectation for these papers, is that you use shorthand wherever you can and not give such lengthy detail to your explanations. Cyclohexane is nonpolar, and therefore it's insoluble, so that accounts for its insolubility in water, which is a polar solvent. Cyclohexanol is polar, and that's because of the OH group. And this compound here, cis cyclohexane 1,2-diol, is also polar. It has 2 OH groups. Also, with solubility in water, there's an inability of cyclohexane to separate the water molecules out. So what you get in a container would be the dense water layer at the bottom, the aqueous layer at the bottom, and the less dense alkane layer or cyclohexane at the top, because there's no miscibility whatsoever, inability to break those hydrogen bonds between the water molecules. Cyclohexanol, sparingly soluble because you can form some hydrogen bonds with the water molecules. So you'll have a water molecule here, and what you'll do is you'll have the OH group from the cyclohexanol, and that OH group can form some hydrogen bonds with the water molecules. So that will separate two water molecules from each other to compete with the cyclohexanol. But one step above that, the cis cyclohexane 1,2-diol has the ability to form hydrogen bonds with two different water molecules. And as a result, then you can separate more of the water molecules out, and therefore the solubility of this compound is even better. The same concept here is key to explaining why the melting point. So if we talk about melting point now, melting points, the bonding between individual cyclohexane molecules, will be very weak intermolecular bonds. These are induced dipoles, also referred to as instantaneous dipoles. Basically, temporary dipoles that exist just purely based on the size of the molecule and the number of electrons. So electron density is the key thing here. They're the weakest of the intermolecular bonding types, so very easy to break. 7 degrees Celsius to melt cyclohexane solid. If you want to look at cyclohexanol, well, in this case, you have the ability to hydrogen bond. So you can hydrogen bond with another cyclohexanol molecule, and these are stronger bonds. Therefore, it takes a bit more energy to break them. And then one step up again, if you have the cis cyclohexane 1,2-diol, you have the ability for two of those hydrogen bonds to establish themselves, and therefore you get a little bit more energy again, well, quite a bit more energy, 98 degrees Celsius to melt that compound. So that is part A. We can quickly look at the answers just to check we've covered everything. Cyclohexane is a non-polar molecule. Forces of attraction between the molecules are induced dipole forces, which will be dependent on the size of the electron cloud. Cyclohexane is not soluble in water, since there is little interaction between the water and the hydrocarbon molecules, so the hydrogen bonded network in water remains unbroken. Cyclohexanol, on the other hand, has an OH group, which allows the molecules to hydrogen bond to each other. Covered that. These bonds are stronger than the forces between the hexane molecules, so the melting and boiling points are higher. The solubility of cyclohexanol is greater than for cyclohexane, since the cyclohexanol molecules can hydrogen bond to water molecules. We covered that. However, the hydrogen bonds between the water molecules and between the cyclohexanol molecules are stronger than those between the cyclohexanol and water, and hence it is only sparingly soluble. That sounds a bit confusing, but basically comparing cyclohexanol to cis cyclohexane 1,2-diol, the key point is that there are two OH groups for this compound. This provides two places for it to hydrogen bond to other molecules, so this increases the force of attraction, increasing the melting and boiling points, and also it's very soluble in water because of the increased hydrogen bonding capacity. So let's go and take a look at part B. Okay, question 2, part B. A year 11 student carried out an experiment to compare the energy released when octane and ethanol were burned as fuels. Octane was found to release considerably more energy than ethanol. The student concluded that this was because octane was a larger molecule, and so there were more chemical bonds to break, and hence more energy released in the reaction. Discuss the misconceptions in the student's explanation and use appropriate data from the table below to provide your own answer for the observation. You're also given the molecular mass of octane and of ethanol. So this is definitely a bond energies calculation, but what you need to figure out first of all is what chemical reactions we're actually looking at here, and then you can work out the enthalpy for the reaction and then figure out the energy produced for each of these reactions and just compare them. So it's when I first saw this question, I thought there must have been some sort of catch to it, but it's a very straightforward question, and let's take a look at how we do it. So I have a split page view here, so we can just keep the numbers beside us as I write. The two equations we're looking at, the key thing here is that we're talking about burning fuel, so this is a combustion, and we're talking about energy as the final thing that we want to determine. So what I've done here is I can do the octane over here, so combustion of octane I can do here, combustion of octane, and then I can do versus combustion of ethanol. So we need to write down our balanced equations. Excuse me. So we're assuming, first thing we need to say is we're assuming complete combustion. So we assume complete combustion, and if we do so, then we can talk about both of these reactions forming carbon dioxide and water. So octane is C8H18, and we're reacting it with oxygen, and we're forming carbon dioxide and water. For the ethanol, we have CH3, CH2OH plus oxygen, and again we're getting CO2 and water if we have complete combustion. We want to balance those equations up, so we end up with 12.5 oxygens here, and 8 CO2 and 9 H2O. And then for this equation we have 3 oxygens and 2 CO2 and 3 H2O. So with your balanced equations, then we can then use the formula. The enthalpy for these reactions can be worked out by summing the enthalpy, the bond enthalpy for the bonds broken minus the sum of the bond enthalpy for the bonds formed. So that's the key to working these numbers out. And then all you need to do is determine the number of bonds broken on the left-hand side and the number of bonds formed on the right-hand side for both equations, and then compare the numbers at the end. So again, very straightforward question, as I say. I'm going to scroll down a bit here. So we now have to draw out these molecules. I always tell my students to take the condensed formula and turn it into a structural formula, so you can clearly see the bonds that are all being broken. So we have 8, 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons in a row. Put all your hydrogens on there. Seems a bit tedious, but at least if you show your workings and you make a mistake in one of these calculations, you'll still pick up attempt marks. So we put all our hydrogens in. That one just there. Okay, so that's octane. We also have 12.5 moles of oxygen molecules, which is a double bond. And then for bonds formed, we're talking about, we'll just scroll down a bit more. For bonds formed, we're talking about carbon dioxide. So that's a double bond, and we have 8 of those, 8 moles of those. And then we also have our water molecule, and we have 9 of those. So let's just take a look at the ethanol situation. The ethanol situation, we have CH3. So we draw that out, full structural formula. Bonded to oxygen, which is bonded to hydrogen. And for our oxygen molecules, in this case, we have 3 of those, 3 moles of those. And then for compounds which are formed, we have our carbon dioxide. We have 2 of those, 2 moles of those. And then for our water molecules, we have 3 of those. So that's we've identified all the bonds to be broken and to be formed. Now, some teachers teach this in that you just identify the actual bonds which are broken and the actual bonds which are formed, but that could sometimes catch you out. So I like to teach the safer method, which is to just assume that every single bond is broken. So all of these bonds are broken and all of these bonds are formed, and then you should come out with the same answer. So let's go through let's do the accounting now. Okay, so for our octane, the enthalpy for this reaction is going to be equal to the sum of our carbon-carbon bonds, which, if you add them all up, there are 1, 2, 3, 4, 5, 6, 7 of those broken, plus the carbon-hydrogen bonds, which, if you add all these up, you have 18 in total, plus your 12.5 times the oxygen double bond. Okay, so that's everything for the bonds broken. Subtract from that the total bond energy for the ones formed. So that's the C double bond O. You have 8 times 2 of those, that's 16 altogether. And then plus the OH bond in water, you have 9 times 2 of those, which is 18 altogether. And if you do that calculation out, you need to use the values. Obviously, for each of those bonds, you get the values in the table, which is the table which is here. So I'm not going to keep referring back to that table. You can look at it yourselves, have it printed out, as I say, if you're listening to these videos. But you take the values for all those different bonds, and your final enthalpy for the reaction there works out to be minus 5099 kilojoules per mole. Let's do the same situation then for the ethanol. In the ethanol, the enthalpy for the reaction is going to be equal to your carbon-carbon bond. There's only one of them to break there. Only one of them to break right there. Plus your carbon-hydrogen bonds, which you have 1, 2, 3, 4, 5 of those. Plus your carbon-oxygen bond, you have one of those. And then plus your oxygen-hydrogen bond, you have only got one of those. Plus your oxygens, which you have 3 of those, and that's bonds broken. So we counted for all of those bonds, and then subtract from that the total bonds formed, which will be the carbon-oxygen. You've 2 times 2 of those, you've 4 altogether. Plus you have the OH bonds, you've 3 times 2 of those, so you've 6 altogether. And that gives you an answer, enthalpy for the reaction of minus 1263 kilojoules per mole. And the final thing is to just change them into energy values. And this is where the molecular mass comes in that we were given in the question. So we were given the molecular mass for octane and the molecular mass for ethanol. So if you divide the enthalpy for the reaction by the molecular mass, you'll get the energy per gram of each of these fuels. So minus 5099 kilojoules per mole, if you divide that by 114 grams per mole, you get an energy for the reaction of 44.7 kilojoules per gram, versus if you take the ethanol's enthalpy for the reaction and divide it by its molar mass, which is 46.1 grams per mole, you'll get an energy for the reaction of 24.5 kilojoules per gram. Okay, so it's clear that there's more energy for the combustion of octane versus the combustion of ethanol. And the reason for this really is it's the type of chemical bonds which are being broken, and the moles of these bonds which are being broken that influence the difference in energy. The NCA guys say here the net bond breaking and net bond making for octane releases a larger amount of energy. So that's your answer to question 2, part B. Very straightforward question, would have been easy marks.